welcome to Lessons in Logic, video number 35, I think. And I'm sort of excited to get to abbreviated truth tables, but we need one more video before we can get there. This is going to be a video on proposition form and tautologies and contingent versus contradictory versus logical equivalence in contradictory propositions versus contingent propositions versus propositions that are logically equivalent. So this appears, I think, this ordering in my notes because a lot of the textbooks like to give us truth tables for these things to illustrate this. I think that would be a good idea, so I should probably do that myself. So I'll see if I can set up a truth table for each of these propositional types we're going to look at. And I suppose I'll want 3 rows and 2 columns for the first one. But before we get there, let's talk about what we're talking about and why we're talking about it. Why are we talking about this? Well, it's a part of the study of logic. It's not strictly speaking testing arguments to see whether the premises provide good support for the conclusion, but it's really important. It feeds into that. In fact, let me rewind to places I never even rewinded to, even in the first videos in the intro unit to this Lessons in Logic series. The most fundamental lessons in logic, I think, are things like these observations about statements or propositions. Propositions convey information. It is possible to use a proposition to refer to a thing. Propositions convey information about things. Propositions have relationships to each other. Obviously, well, I hope it's obvious. If not, know it now. Obviously, with validity, with that quality of argument such that it's not possible for the premises to be true or the conclusion false at the same time, what we're interested in is the relationship among propositions such that the premises in an argument are propositions that guarantee the conclusion. We're interested in that relationship. The premises entail the conclusion. That's one relationship among propositions we're interested in. But there's also probability relationships where the premises of an invalid but strong argument, rewind to the intro unit if you don't know what all these terms mean, an invalid but strong argument, the premises of such an argument render their conclusion probable. They have that relationship, a relationship such that the premises provide some good support without quite guaranteeing the conclusion. And so statements refer to things and they convey information about things, and they are relative, they have relationships to each other. That's at the most fundamental level what logic is all about, I think. Now, what we're doing here in this video is looking at a few relationships statements have to each other, and characteristics of statements. The statements of characteristics are terribly important. All right, that's enough of that. Let's look at a few statement characteristics and relationships and do some truth table illustrations of them, and then move on in the next video next week to abbreviated truth tables, which are super awesome. All right, statements have forms, i.e. patterns, like arguments do. Statements have patterns, arguments have patterns. Here's a definition from a textbook, and which textbook? Maybe all of them. But if my notes don't say and my memory doesn't say, it's a good bet that I'm getting this from Copey's Introduction to Logic. A proposition form or a statement form is a sequence of symbols containing proposition variables, which are lowercase letters, but no propositions, such that replacing the proposition variables with propositions makes a proposition. Wow, that was a lot of text. Well, proposition variables means those lowercase p's and q's when they're italicized that I keep using. Let me see if I can just put this into more ordinary words. A proposition form is a symbol for the pattern of a proposition. Now I realize I don't like that, because I don't even think this is a proposition form. This is symbolized proposition form. So I don't like this definition. Let me see if I can just replace this. Let's see. Oh yes, all you really need to do is observe statements have forms. They have patterns. Statements have forms or patterns, like arguments do. We can symbolize these forms to study the patterns. Let me say, we can symbolize the patterns in order to study them. Or we can symbolize the forms in order to study them better. All right, if we carefully stick with the usual conventions, if we stick with the conventions, we will use capital letters to symbolize atomic propositions, and those are the propositions not made of any other propositions. We will use lowercase and italicized. We will use lowercase and italicized letters to symbolize lots of propositions. And therefore, noting that we will also need to give a scheme of abbreviation or legend or key saying what letter symbolizes what proposition. And therefore, we will use capital letters on specific statements, but lowercase letters when we're representing more generic forms or more generic patterns. I like the word pattern better than form. Okay. Statements have patterns. We can symbolize these patterns to study them better. And the patterns are generic. Lots of statements will fit a pattern. So here's a statement pattern, simple statement. P. It's just an affirmation. Any affirmation of a proposition that's not made of other propositions. P, lowercase, can symbolize the statement, I am drinking tea, or the statement, the tea in the teacup is hot, or the statement, the darn tea kettle is mostly empty. The darn electric kettle is mostly empty. Or the peanut jar is 3/4 empty. The proposition P dot Q, meaning P and Q, symbolizes conjunctions like the tea kettle is mostly empty and the jar of peanuts is mostly empty, or the teacup is, the tea is hot, but the water in the water cooler is not hot. Those are conjunctions. Those are statements of two statements. And then there's the negation pattern. The tea is not cold. The time is not still in the morning. The rain has not yet reached HKBU's Kowloon Tong campus, though it appears that another round of rain is coming from somewhere else. All right. Those are statement patterns, and they're generic. Lots of statements have them. But if I give you just a capital letter, it'll usually, if I'm doing things right, it will always stand for a specific statement. These are just our customs for how we symbolize things. If you get them mixed up, it won't do you much harm in the study of logic. Now, a proposition using a certain proposition form is called a substitution instance of that form. And now let's start getting to the point. A tautology is a proposition whose proposition form has no false substitution instances. In other words, a tautology is a proposition that cannot be false. Now, if I was giving you the form of a proposition, I wouldn't give you A or not A here. A wedge tilde A, meaning A or not A. I give you P or not P lowercase, P wedge tilde P, meaning either P or not P. That is a tautology, and it stands for every such tautology that has that pattern. This stands for either the rain has reached the Kowloon campus, or it is not. Either the tea kettle is nearly empty, or it is not. Either the peanut jar is mostly empty, or it is not. Either the tea is hot, or it is not. Either Mark is tired, or he is not. This P lowercase wedge tilde P symbolizes all propositions that have that pattern. It symbolizes that pattern for all propositions. But A wedge tilde A, uppercase, no italics, means specific propositions. Which one? Well, whichever one we say A is defined as. And if we're being, if we're going to be careful, we'll say what A means. Let's say A means Mark is grateful for his nice caffeinated cup of tea. Mark is grateful for tea can be A. Either Mark is grateful for tea, or it's not the case that Mark is grateful for tea. That's the atomic proposition here. Now, we can illustrate with truth tables to see why tautologies are always true. It's really very simple. A is either true or false. And either way, A wedge tilde A is going to be true. If we wanted to, I'm really not going to keep doing this, I think, for every truth table we make in this video, but we could, if we wanted to, add some columns. How many would we need? 1, 2. We would need 2 columns. Nope, we would need 1 more column. And we could symbolize every symbol in this proposition, keeping in mind which is the main proposition symbol. Here's our guide column for A, and here's our symbol for the proposition as a whole, the main operator in the proposition. So A is true or false. Tilde A is false or true, and either way A is true. So there's no possibility for this proposition to be false. That's what we've just illustrated with the truth table. Now, a contradiction is a proposition whose proposition form is no true substitution instances. In other words, a contradiction is a proposition that cannot possibly be true. Now, I could do this for the form by using lowercase italics, or I could do this for a specific proposition using uppercase no italics. I think I'll do specific proposition. And again, I'll define which proposition I'm talking about. It doesn't much matter which proposition I'm talking about. Nevertheless, I'll tell you which proposition I'm talking about. I'll talk about the same proposition. Mark is grateful for tea. So it is false that Mark is grateful for tea and not grateful for tea at the same time. Suppose Mark is actually grateful for tea. Well, then Mark is grateful for tea. Mark is grateful for tea. It's false that Mark is grateful for tea. And it's false that both of these things are true at the same time, that Mark is grateful for tea and is not grateful for tea at the same time. Or suppose Mark is not grateful for tea, then, well, again, Mark is not grateful for tea, Mark is not grateful for tea, and it's true that Mark is not grateful for tea. But it's false that Mark is grateful for tea over here in this column, and therefore, what goes here, clearly false. It's false that Mark is both grateful for tea and not grateful for tea at the same time. That's a contradiction pattern. A contingent proposition is a proposition whose proposition form has some false and some true substitution instances. In other words, some rows of the truth table will be true, some will be false. And here, there's literally an infinite number of contingent propositions. So I'm just going to illustrate the form here. In fact, I'll illustrate several in a row. These are all contingent proposition forms. Some substitutions are true, some are not. In other words, some propositions that have the pattern Hang on. 1, 2, 3, 4, 5. 1, 2, 3. Some propositions having the pattern P wedge Q are going to be true, and some are going to be false. Some propositions having the pattern P dot Q are going to be true, some are going to be false. Now we could illustrate this with specific propositions. Oh darn, I didn't copy the right thing there. There we go. P wedge Q, P dot Q. Either the teacup is hot or the electric kettle is hot. The teacup is hot and the electric kettle is hot. Those are both true right now. But here's some other propositions with the same pattern. Either Mark is in London or Mark is in Harare, Zimbabwe. Mark is in London and Mark is in Harare, Zimbabwe. Well, neither of those things is true, so those are both false. Hang on, let me think. What did I just tell you about contingent propositions? Was I talking about propositions or proposition forms? A propositional form can be contingent if some propositions. Oh, yes, that's well put. I like how it's written here. Let's go with that. The contingent proposition is a proposition whose proposition form is some false and some true substitution instances. Yes, that's right. So those are contingent propositions because it's possible for them to be true and it's possible for them to be false. So it's better if I just stick with this pattern. A contingent proposition is a proposition whose pattern does not guarantee anything about its truth or falsity. That was better. I like that. Contingent proposition is a proposition whose pattern does not guarantee either that it's true or that it's false. Example. I guess if I'm going to do this, I should have one for just plain old P there. P could be true, could be false. Some propositions with that pattern are true, some are false. Actually, this is a pattern for every proposition. P or Q, some are true, some are false. P and Q, some are true, some are false. Some propositions having those patterns are true, some are false. Okay, a biconditional proposition is an if and only if proposition. It's true if its components have the same truth value, otherwise it's false. Oh, wait a minute. Just a moment. This is not in the right order. This is something we went over in an earlier video. Textbooks go over this material in a weird way sometimes. I think that's why it's here in my notes, but it shouldn't be here in my notes. I did put it in the right place in my notes, but apparently I never Control-X'd. I just Control-C'd or something. So anyway, never mind that. Let's go to logical equivalence. Two propositions are logical equivalent. Oh, that's why I was here. Two propositions are logically equivalent if their relationship is such that the tribar statement of them is a tautology. In other words, two logically equivalent propositions mean the same thing. Now, tribar is that symbol for if and only if. So let me try to say this in a third way. Logical equivalence is the relationship among two propositions such that if you say one and then say if and only if and then say the other one, the whole thing is going to be a tautology. It can't not be true. In other words, they're always true at the same time or they're always false at the same time. That is logical equivalence. Or maybe we should say it this way. Two propositions are logically equivalent if their patterns are such that if one's true, the other's false, and if one's true, the other's true, and if one's false, the other's false, and vice versa. All right, so double negation is logically equivalent. Double negation is, let me rephrase that. Let me rewind rather than rephrase and just state this. Let's look at some important logically equivalent propositional forms. Here are two logically equivalent forms. Double negation means tilde tilde p is logically equivalent to p, or the negation of negation is the same thing as the thing negated. De Morgan's theorems are that the negation of a disjunction is equivalent to the affirmation of the conjunction of the negation of both disjuncts. Or the negation of a conjunction is logically equivalent to the conjunction of the negation of both conjuncts. I think I said that properly, but who knows? What that means is not both means the same thing as not one, not the other, or not either means the same thing as not one or not the other. In other words, it's not true that DeSantis will be president, or, well, that seems so plausible. I want to work with plausible propositions. So let's not negate a plausible one. Simple plausible propositions is what I want. Hang on. It's not true that either Bernie Sanders will be president or my brain's freezing as I try to remember the name of some politician who I think is highly unlikely to be president anytime soon. I'm recording this in the year 2022. I'm getting my names mixed up. I want to try, there we go, Lynn Cheney. Lynn Cheney, not likely to be a Republican president anytime soon. That's the name I was looking for. It is not likely that either of them will be president. So I'm illustrating De Morgan's theory with I'm defining De Morgan's theory with a convenient example. It is not true that either Bernie Sanders will be president or Lynn Cheney will be president is logically equivalent to it is not true that Bernie Sanders will be president, and it's not true that Lynn Cheney will be president. How about I'm getting the names wrong? I'm suddenly getting confused about the names of politicians. All right, so now De Morgan's other theory. Let's see. This is the one where it makes more sense to say DeSantis. It is not the case that DeSantis will be president in 2025 and Kamala Harris will be president in 2025. That means the same thing as it's not the case. Either it's not the case that DeSantis will be president then, or it's not the case that Kamala Harris will be president then. Not both means either not one or not the other, and not either means not one and not the other. Finally, the horseshoe. P horseshoe Q is logically equivalent to tilde P wedge Q. In other words, if P then Q is logically equivalent to not the if clause or not the then clause. In other words, to illustrate by example, if it is pouring down rain when Mark leaves the office, then Mark will bring the umbrella, is equivalent to either it is not pouring down rain when Mark leaves the office or Mark brings the umbrella. They mean the same thing. Now let me illustrate with a few quick truth tables and we'll be finished. I want 3 rows for this, and I really only need 2 columns. Now, if we wanted to, we could put in extra columns here. We'd have a TF for the P column, and then an FT for the tilde P column, and then a TF for the tilde P column. Anyway, the point is, a proposition and its double negation mean the same thing because they're always true and they're always false in the same circumstances. Now, P wedge Q De Morgan's. Okay, this will be a little more involved. I'm going to need 5 rows. How many columns? 1, 2, 3, 4 columns minimum. Well, this might get complex. 1, 2, 3. Let's add some extra columns here. Now, tilde P wedge Q we have to understand these two go together. And without doing a little more work with Microsoft Excel, I don't think we can do the formatting here just right. All right. How did I get confused about how many columns I would need? I still need another column or two. All right, so now let's bear in mind these go together. Maybe we will color code them. That might help some of us. Let's make it some sort of darkish blue. Now, tilde P dot tilde Q. Silly me, I only needed that many columns. Okay, so there's one of our statements in blue. There's another one in red. And we want to see is that they mean the same thing. So P and Q could be true or false in these ways. And when P or Q is true, P wedge Q is true. And when they're both false, it's false. So that dot there, that tilde there is going to be the opposite truth value. So not P or Q, not either, is false, except when they're both false. Now, tilde P is going to be false when P is true. Tilde Q is going to be false when Q is true, and true when Q is false. Well, this doesn't feel right. Hang on. Okay, tilde Q, TFT, FFT, FT. Good, good. These columns look right. Now, these columns, do they look right? FFT, TT, DFF, they look right. Now, the dot. False, 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 and true. And what do we learn? We learned that in these main columns here, these are the columns we really care about here, we have the same truth value. For every possible arrangement of whether the constituent propositions of these De Morgan's equivalences here, for every possible arrangement of whether the constituent propositions are true or false, this proposition and this proposition are going to be true or false at the same time. They have the same truth values. Therefore, they are considered logically equivalent. Now, I do believe I can copy and paste for the next De Morgans and then just make some quick adjustments. Let's make this one a dot. And then let's make this one a wedge. Straighten out our color coding and check our work. That's the wrong blue, isn't it? All right, tilde P dot Q, logically equivalent to tilde P wedge tilde Q. Now, if it helps, put some parentheses around some of these things. All right. So now let's fill in these boxes properly. We're going to find the same things in these two columns. When P and Q are both true, the affirmation that they're both true is going to be true. Otherwise, it's false. So this is going to be true and then false, false, false. Tilde P is going to be the opposite of P. Tilde Q is the opposite of Q. And the disjunction of tilde P and tilde Q, the statement that one or the other is true, is going to be true except when they're both false. So it's going to be false, triple true. Now here, this is going to be, this tilde column, this negation column is going to be the opposite of that which it negates. It's negating true, triple false. So it's a false, triple true, well, triple true. And therefore, for every possible arrangement of whether or not the constituent propositions of these two proposition forms are true or false, they're always going to have the same truth value. And then horseshoe. Let's see, for horseshoe, we're going to want a simple five-row truth table with 1, 2, 3, 4 columns. Let's try with 4 columns. See how that works out. So our atomic propositions are P and Q. We like to italicize them because that's proper, and we like to bold them to indicate these will be the guide columns. And as usual, I feel like filling this in first. It's going to be TTFF and then TFTF. Now P horseshoe Q and tilde wedge or Q. We want an extra column. I think we just might want 2 extra columns. All right, P horseshoe Q is true except when P is true and Q is false. If P, then Q is true except when P is true and Q is false. An if then proposition is true except when the if part is true and the then part is false. So that's going to mean the same thing as this, which we'll color code with blue. Now let's make them blue and red, left and right again. Wasn't planning any political convergence there, correspondence there, but it worked out. So TF when Q is true, and when Q is true, duh. When Q is false, Q is false, duh. Tilde P, that's going to have the opposite value of P. When P is true, its denial is false. When P is false, its denial is true. So now the wedge column here. Now it's going to be the same results as this column. It's going to be TFTT. That's pretty much guaranteed because these are logically equivalent propositions. But let's not think of that way. Let's think this way. Is a wedge true? Is a disjunction true when one disjunct is true? Yes. If it's true either that this tilde P or that this Q, then we put a T here in this column. If one of them is true, then the statement that either one or the other is true, and it's false otherwise. So basically we have, again, true, false, true, false. Bearing in mind, and rewinding to watch earlier videos, if necessary, that we're using the inclusive or. We are assuming that wedge does not exclude the possibility that both disjuncts be true at the same time. And that's it. Next video, I think we're finally getting to abbreviated truth tables. See you then.